Hello, my name is Aldo. I'm doing my master's at the University of Ottawa, and I'm working with Professor Jeff London. And today I want to talk to you about an experimentally simple method to weakly measure quantum incompatible observables. You might have heard quantum mechanics is counterintuitive. Well, quantum measurement is not the exception. Just to put an example, let's consider incompatible observables. So incompatible observables are those for which the order matters. Measuring A and then B is different from measuring B and then A. A typical example is position and momentum, for which the uncertainty principle tells us that we cannot have a perfect knowledge of both of them simultaneously. Measuring one of them is going to collapse the wave function and erase the information about the conjugate variable. However, joint measurements of incompatible observables are useful. With them, we can study the dynamics of a quantum particle and try to answer questions like, what is the role of time in the quantum domain? We can also study paradoxes. Perhaps the most famous one is the EPR paradox, which deals with entanglement. So entanglement is a signature of quantumness and is central for quantum information processing. Another application I'd like to mention is quantum state reconstruction or estimation. Okay, so first I'll introduce the tool of wiki measurements, and then I will mention this application of quantum state tomography to finish with our work in which we measure products of incompatible observables with one readout system. So in a measurement, we have our quantum particle and we need a readout system that tells us one value. The characteristic of a weak measurement is that the coupling between the particle and the readout is made very gently, so that we avoid the collapse of the wave function. In that way, we can perform measurements in sequence, even of incompatible observables. How to perform a wiki measurement? The very first implementation of a wiki measurement was done with photons polarization. The readout system was the profile of the photons described by some width sigma. We need a birefringent material, such as calcite or a BBO crystal. This material is going to displace one of the polarization's components, let's say horizontal polarization, by an amount delta. If delta is much larger than sigma, then we can distinguish H from B, and we're in the strong measurement regime. On the other hand, if delta is much smaller than sigma, then we are not able to distinguish anymore H from B. And in that case, we are performing a weak measurement. One of the applications of weak measurement is the state reconstruction, in which the idea is to perform a sequence of weak measurements to retrieve the wave function, density matrix, or quasi-probability distribution that describes the state. This is an interesting application because this can be used as a verification procedure in quantum physics. Imagine you are doing a very complicated experiment, that you know what to expect at the output of it. In that case, you can reconstruct your state at the output of your setup and see if it is working properly or not. Also, these measurements give us an operational definition of the wave function, density matrix, or quasi-probability distribution, which are usually complex quantities. This field has some past, and it is called quantum state tomography, in which the idea is to perform an over-complete set of measurements to retrieve the quantum state. The problem with this method is that you need to solve an inverse problem, which becomes harder as your system becomes more complex. So it could be great if we could have a direct scheme that tells us your state without having to solve a hard problem. A survey of methods can be found here. Some of them have been implemented. In these implementations, we need one readout system per observable, which makes experiments difficult. Why? Because readout systems are useful degrees of freedom of the quantum particles. And the quantum particles don't have many degrees of freedom. For example, a photon has the spatial mode, the time, the frequency, and the polarization. We often want to use those degrees of freedom to perform information processing tasks, such as quantum key distribution. So it would be great if we could have a method to perform a state reconstruction with less resources. And this is where enters our work. So we are working with photons polarization, and remember the degree of freedom we are using is the spatial profile of the photons, which has two dimensions, x and y. So we will use only one of them, let's say x. So by using lenses and looking at the far fields of our beam, we can also see the momentum distribution, which is sometimes useful. Okay, this is the question that we want to answer. Can we extract information of two observables with one single readout system? The answer is yes, but you need to measure higher order parameters of the readout system, for example x squared, and also you need to measure more aspects of it, for example d, which is x plus p. So do we have access experimentally to that? Okay, so let's remember. So we have our beam of light, which has a spatial distribution in one plane. We know that we can go to the far field by using one lens to get the momentum distribution. So we need this configuration right here. But what happens in between? Here we are looking only at the two planes, the input plane and the output plane. In between, x and p get mixed. So there must be one plane in which we can get the distribution of d. And that is called a fractional Fourier transform. So the idea is quite similar to the Fourier transform. We have the spatial distribution in one plane, and then a distance L, and then a length of focal length f, and then more free space propagation by a distance L. At the output, we have the distribution of this quadrature, which is x cosine of theta plus p sine of theta. L is going to be a function of the angle theta. So to go to D, we need that theta equals 45 degrees. Okay, for example, if F equals 1 meter, then L is roughly 29 centimeters. So we have a way to measure D. So that's great. That means we can incorporate it in our experiment. So this is how the experiment looks like. So initially we prepare the photons polarization. We perform algorithmic measurements with BBO crystals and with the help of halfway plates. And finally we can get the X, P, and D distribution by using some lenses. As a proof of the method, we measure polarization states of photons. Here we have the Bloch sphere, in which we can draw any state of polarization of photons. So we send linearly polarized photons, which are described by this density matrix. By performing weak measurements of incompatible observables, we can extract every entry, even off-diagonal terms, of the density matrix. As a summary, measuring this product of incompatible observables is a useful tool in quantum physics and quantum information. The fractional Fourier transform can be implemented in an optics lab, and it allows for new and unique measurements which might be interesting for different applications. So we demonstrated a method for performing joint measurements of incompatible observables that requires one single readout system. This method naturally incorporates a quadrature G. So as a proof of principle, we apply the method to obtain the entries of the density matrix of photons polarization. I hope you have enjoyed this video, and thank you so much for watching.